es líder del grupo de alta energía de esta institución. Su área de investigación es la física teórica y experimental de partículas elementales o altas energías. Su investigación en la línea teórica se centra en la física de neutrinos, astrofísica, con énfasis en la búsqueda de señales físicas, más allá del modelo estándar. Y hoy nos va a presentar el tema titulado Explorando nueva física utilizando neutrinos. Principal Professor at PUECP and leader of the High Energy Group of this institution. His research area is theoretical and experimental physics of elementary particles, or high energies. His research in the theoretical light focuses on neutrino physics, astrophysics with an emphasis on the search for physics signals beyond the standard model, and today he presents the topic entitled Exploring New Physics Using Neutrinos. Alberto, buenas tardes. Te agradecemos tu participación y puedes iniciar tu presentación. Gracias.
Hi everyone. Thank you for the introduction to Jorge, and thank you for the invitation to the organizers. So I am going to present my talk. Let me 1 minute.
Okay.
Let me 1 minute, since I miss the window. Let's see. Okay, it's here. Are you seeing my talk? It's going to start.
Yes, yes.
It's going to start.
Yes.
It's going to start. Please let me know if you are seeing something.
Yes, we can
Jorge,
see.
please. Yes?
Yes.
It's
Yes,
fine?
yes.
It's full screen now. Okay, so I can start. So, please, there is a problem?
Solo se está viendo el PowerPoint.
Yes, sí, lo he puesto para pantalla completa. ¿Hay problema que lo ponga pantalla completa?
Ya. No, solamente le menciono porque se está viendo ahorita solamente la base del PowerPoint. O sea, no sé si es que de repente está cambiando de slides.
¿No se ve un título? ¿No se ve el título?
Sí, sí se ve.
¿No se ve Exploring New Physics Using Neutrinos? ¿Un título así?
Sí, se ve, Alberto, sí se ve.
Ya. A ver, voy a pasar la segunda slide solo para... ¿Lo ven? Pasé el segundo slide. ¿Lo vieron? ¿Lo están viendo?
No ha pasado.
He pasado el segundo slide.
No, aquí no se observa, Alberto.
Espera un segundo, qué raro. Estoy compartiendo la ventana. A ver, un segundo. Estoy compartiendo la ventana. A ver. Un segundo, voy a hacer algo, ¿ya? ¿Lo están viendo ahora el PowerPoint?
Sí, la presentación.
A ver, voy a ponerlo, lo estoy poniendo en pantalla completa. ¿Lo ven ahora de nuevo? ¿Sí?
Sí, se ve el título.
¿Y ahora?
Sigue el título.
No sé, ¿alguna idea? Porque yo estoy pasando las slides, o sea, y si lo paso acá, ¿acá sí lo ven?
Sí.
Ya. Ok, tengo un problema. ¿Alguien sabe por qué no se ve el título, por qué no se ve en pantalla completa? ¿Hay alguna cosa que tenga que poner en pantalla completa para que se vea? Porque cuando lo pongo en full screen no lo están mirando, porque yo empiezo a cambiarlo en full screen. ¿Alguna sugerencia?
Sí, no sé si me logran escuchar.
Sí, te escucho bien.
Ya. Cuando usted comparte pantalla en el Google Meet, aparecen dos opciones, que es la de compartir pantalla completa o compartir una ventana.
Ajá, yo estoy usando ventana.
Y claro, denle la opción de compartir pantalla completa para que
cuando usted pueda
ponerla, claro.
Ok. Ese es el problema, Ok, gracias. Lo voy a hacer. Voy a dejar de compartir un momento. Ya, entonces voy a hacer ahorita, presentar ahora, pantalla completa. Ya, y compartir. ¿Ahora se ve? Ya está en el outline, ¿no?
Exacto, está en el outline.
Yeah, yeah. I'm sorry for the technical problems. So, well, the title of my talk is Exploring New Physics Using Neutrinos. Well, I am going, since this is a meeting with several lines of physics, I am going to give you an introduction about particle physics, a very, very brief, and also a brief introduction about the neutrinos, history and sources, and then I'm going to try to explain you and in much more detail the oscillation induced by mass and the search of new physics through quantum decoherence, which is the goal of my topic, no, of my talk. So, well, the context of neutrino physics is elementary particles. The neutrinos are one of the elementary particles. We have the periodic table, and we have the corner torque of matter of matter, which are the elementary particles. We have leptons and quarks, and also we have the force mediators, the photons, gluons, boson C and W, and the Higgs boson. For instance, something that I assume you know, that the ordinary matter is made up of quarks ups and downs and electrons. And well, we have here the size of the atoms, nucleus, protons, and the quarks, some idea. And also, this is the context elementary particles. So we have also the fundamental forces mediated by the gauge bosons. Well, gravitational is not included in the description of the Standard Model. I am mentioned only to give you an idea that we have forces which are within the reach of our sense, which are the electromagnetic force or the gravitational force, and they are all forces of short range. One is the weak force, which is responsible of the radioactive decays, and also the strong force, which is responsible to have that we have composite particles by quarks. No, the quarks are glued by the gluons, and the gluons are the mediators of the strong force. So this is the context. So, well, the way what we describe mathematically, this is assuming an action at distant forces. This is through fields, and this is described within the so-called Standard Model, which describes as the interactions and particles. This is the Standard Model. Well, of course, we are not going to discuss the equations. This is only to show you. And well, let's start with the neutrinos. The neutrinos, as I said, are within the Standard Model. We have three types of neutrinos: neutrino electron, muon neutrinos, and tau neutrinos. In fact, there is a way to measure the active neutrino that it has been done time ago, confirming that we have only three active neutrinos. So also the neutrinos interact via weak interactions through the boson W and boson C. Here, let me see. Here I am showing you the interaction from neutrinos, and they interact very weakly with matter. In fact, we can make a calculation of the mean free path of water for 1 MeV neutrinos, and we find that it is 10 to 17 centimeters, which is equivalent to 0.1 light years or 10 millions of Earth diameters. So they interact very weakly. Within the assumptions of the neutrinos, within the Standard Model are massless particles. We are going to return to this point at some point of the discussion. So the neutrinos were inferred, or I mean the existence of a ghost particle was inferred by Pauli when they tried to observe the electron energy spectrum of the neutron decay. In fact, they expect to obtain a monoenergetic energy spectrum or a two-body decay, and they found a three-body decay. I mean, they found not continuous, not this monoenergetic energy spectrum for the electron. They found a continuous energy spectrum. Then Pauli, in order to save this incompatibility, proposed a new particle, which he calls as a desperate remedy for saving energy conservation. This was not a detection of neutrino, the appearance in scene of the experiments of the neutrinos. This is a letter sent for Pauli to a group of physicists in Tübingen in December 1930, saying what I mentioned. So almost 30 years later was built the first experiment able to measure to detect the neutrinos. And this was the first reactor neutrino experiment. Within the core of the reactors, there are a very intense flux of electron neutrinos, and they capture the electron neutrinos through this reaction, and they measure, the gammas produced from the annihilation of this positron, and also the gamma from the capture of the neutron from cadmium. And they identify this kind of neutrinos. Then in 1962, Lederman, Schwarz, and Steinberger was the first to build the first spin-damped neutrino experiment, which the source of neutrino comes from the pion decay. And then they found this reaction. As a product, they found an anti-muon, but they do not see, or they didn't see the electrons or positrons at the final state. So they conclude that this neutrino, which they produce through this pion decay, should be different than this one. And this is the way that was discovered, the muon neutrino. Finally, in 2000, in Fermilab, the donut experiment, the donut experiment observed for the first time nu tau, which was produced through this decay, the meson decay. Then they interact via charge current interactions, and then through tau decay or disking, they observe the tau neutrinos. So this is only one, not very recently, but not so very old. No? It's 2000. So we have several sources of neutrinos. We have solar neutrinos, we have atmospheric neutrinos, we have extragalactic reactors, and accelerator neutrinos. They are different in energy, and they sometimes overlap. And which kind of neutrino we have observed up to now? Well, this is all the sources. All the sources have been observed already, no? But I am going to point out something, some very interesting about some of these sources. So, for instance, the extragalactic neutrinos have been observed for IceCube. In fact, in 2007, they have found a correlation between gammas and neutrinos, and they have identified a source. It's a blazer, which is a nuclear active galactic nuclear, where the particles are going through, are pointing directly to Earth. And they found several neutrinos from this source, and this is IceCube. And this is very interesting because this has been the oldest neutrino has been detected. It's 4,000 million years old. So also neutrinos can be produced through supernova explosion. Well, the stars are in this sort of hydrostatic equilibrium, which is the equilibrium between the gas pressure and the gravitational mass. And then when you have a supernova explosion, in particular the iron core collapse, you are going to produce a lot of neutrinos. And in fact, there has been a very famous event which has been detected, neutrinos coming from the supernova called SN 1987A, because it was detected on 1987 in February, a supernova located at the Large Magellanic Cloud, 100 170,000 light years. So this is a photograph of the detectors, and Masatoshi Kochiba has been a Nobel Prize for observing cosmic neutrinos in general, because he was the leader of the Kamiokande. So, and this is the energy spectrum in order of MeV of the neutrino. So there are also trillions of neutrinos that are coming from the sun. This is a distribution of neutrinos coming from the sun. And in the sun takes place a net reaction, which is the fusion of 4 protons, giving you helium. No? Or in other words, you are fusion hydrogens and you are producing helium. And during this production, you produce also, of course, energy and also electron neutrinos. This is, these electron neutrinos were, there were several experiments designed to detect this electron neutrino flux. For instance, this experiment Homestake, I'm going to go back. Okay, this experiment Homestake tried to detect these electron neutrinos in order to prove the solar neutrino model. So what would happen? What would happen that several experiments tried to measure this, the electron neutrino flux, and they found a deficit that respect to the electron neutrino flux expected. This has been so-called the solar neutrino problem. So the deficit is going to change from 1/3 to 1.5 of the expected electron neutrino. So this problem was finally solved. There were several experiments that were consistent with this deficit. They didn't know what would happen, and the option was the solar neutrino flux. I mean, the solar standard model was wrong, or the other option was that there were some problem with the neutrinos itself, so a particle physics problem. So in the experiment SNOW, or Sudbury Neutrino Observatory, they observed several reactions. One is elastic reaction, charge current, neutral current, and they found particularly that the total flux of neutrinos, independent of the flavor, was consistent with the expected flux of the standard model. So the deficit was right, but the deficit was in the electron neutrino. But what's happening is that the initial flux was transforming in other particles. They proved that the calculations of the solar standard model was correct, but the problem with the neutrinos was that the electron neutrinos born at the sun were changing in its flavor to another flavor, and then here and there we observe this sort of deficit. So this confirms that the neutrinos suffer a neutrino conversion coming in struggle from the sun. So the R. McDonald received a Nobel Prize for this. There were also several experiments trying to observe neutrinos. They tried to observe proton decay, but in that context, they tried to control or understand the background, which was the neutrinos. And in such regard, they found that some problem. What is the problem? Okay, the cosmic rays hit in the upper nucleus, the air nucleus. In the upper atmosphere, hit the air nucleus, and then they produce pions. And from the pions, you have mu neutrinos and electron neutrinos, if we follow this decay chain. And what was expected was more or less a ratio over 2 was expected between mu neutrinos and electron neutrinos. What they found was that was incompatible with this ratio equal 2. They made this double ratio. Here is the double ratio between the data and the Monte Carlo, and they found that there were a discrepancy with 1, because if you compare Monte Carlo, which is your theoretical hypothesis with the data, and your guess is okay, you should get a ratio equal 1, a double ratio equal 1. They found an anomaly, a discrepancy with 1, and this was called the atmospheric neutrino anomaly. Here is the double ratio. This is the ratio, and this is the double ratio between Monte Carlo and data. Okay, finally, the solution, the puzzle was solved by the Super Kamiokande experiment, which observed in 1988 the neutrino oscillation. Here is a photograph within the detector, and this is the multipliers. And they found that the neutrino were having some kind of transformation, or they disappear. They disappear depending on the distance they travel. So here I'm going to show you the data. I am not going to try to complicate the stuff, but it's relatively simple. We have here the zenith angle, and this is the cosine of the zenith angle. This is 1 is equal when the cosine of the zenith angle is 0. So here is the zenith angle. So when they come from above, you have 0. Then they come from below, you have pi. So we have cosine theta c equal to -1. So in short, so when you have 1, you have 10 kilometers of the travel distance for neutrino. When you have -1, you have 13,000 kilometers. So the distance is different. Okay, so this is data, and this is Monte Carlo, and this discrepancy was explained for the so-called survival probability or disappearance probability. In the other case of electrons and muons for other energies, it was not so dramatic. The discrepancy was more or less the same. Here is more or less the same. As I said, the points, the dots, and the bars are the data, and the full line is the Monte Carlo. So this discrepancy was explained for the neutrino oscillation, for the phenomenon called neutrino oscillation. So this solution of atmospheric and solar neutrino has, there were several theoretical hypotheses competing for solving these problems. I mean, I am going to tell you which is the main one, but in principle, at that moment when the data were released, there were several theoretical hypotheses competing for explaining these discrepancies. And one of them was, let me show you one of them was supposed that the neutrino, there were different neutrinos, there were neutrinos coupling, different types of neutrino coupling in a different manner with gravity. And this was some attempt to explain neutrinos. Other one that is going to talk about later is the neutrinos where the neutrino system is within an environment, and the environment is causing some phenomenon called quantum decoherence. This is something that I'm going to explain with more detail later. So another, that the neutrino, when they interact with matter, change its flavor. This is not predicted by the standard model. The flavor should be the same. I mean, it might not change according to the standard model, but beyond the standard model is allowed. So in principle, this was other possible solution. And finally, what happened? The Occam razors work, and the simplest explanation is usually the right one. This is the easy version of the Occam razor, the popular version. So in principle, the main mechanism show with several data that I am not going to talk about here. Show the main mechanism is oscillation induced by mass. Okay, let's start with neutrino oscillations. Well, the idea is, for instance, we start here with this is a sort of probability, survival probability, and this is the appearance probability. And we start, for instance, with a mu neutrino, which is green, And then when the neutrino travel a distance, you can, if you did observe the neutrino, it could change to tau neutrino. And if he travels more, it can go back to mu neutrino. This is the phenomenon called oscillation. An oscillation, as implies the hypothesis which explain better the data, is oscillation induced by massive neutrinos. So this is inspired by Bruno Pontecorvo. Bruno Pontecorvo suggested at first the neutrino-antineutrino oscillations, inspired in some phenomena called tau oscillations. And well, the basic idea, we are not going into the details. I am going to point you out the main ideas. Well, the main ideas is that flavor or interaction eigenstates are misaligned with mass eigenstate. This is the main idea of the main reason. I mean, the reason that you find a neutrino oscillation, that you have this neutrino oscillation phenomenon. Well, if you make your evolution, I mean, you solve your equations, you are going to find the disappearance probability, which are going to depend in the oscillation amplitude and interference phase. This interference phase is going to be the difference between mass square, the mass square 2 and mass square 1. Remember that these mass eigenstates are different from the flavor eigenstates. So this is a very simple version of the oscillation probability. This is only to show you that this is an amplitude for the probability, and this is an interference phase, which is as a function. It's a function of ms of the difference of mass squares of m2 and m1. So this depends on L and the distance between the source and detector and the energy and the neutrino energy. The oscillation wavelength has an inverse dependency with the delta m square. And in fact, if we can visualize in simple terms in the oscillation, we are working the quantum mechanics as its more clear, more basic version, the double slit experiment. Since you can visualize a sort of virtual interferometry between these two eigenstates, the nu one eigenstate with the nu two, which the difference in phase is just a mass, the mass of each of one. So for that reason, this diagram of interferometer are illustrated, these different patterns are illustrated basically the idea at the end, that abstract difference between masses, which is the difference of phase. And this is a quintessence of quantum mechanics, and we can test long-distance interferometry with neutrinos, since the wavelength depends on delta m squared, and delta m squared is inverse of delta m squared, and delta m squared are very, very small. This is a picture of the neutrino oscillation. How about my time? Sorry, can you give me how many time are remaining for my talk? Sorry. Well, I am going to continue. So the three-neutrino oscillation, we have the three-neutrino oscillation paradigma here. And this is, well, we have to add to all the flavors. We have to, this misalignment between all the flavor or interaction eigenstate respect to the three mass eigenstates. And the connection is through a mixing matrix. I think that I didn't mention that before in the two-generation formula, but in the three-generation formula, I'm going to mention this is the connection between them are through this mixing matrix, which is called the UPMNS for the Pontecorvo Máquina Gago-Sakata. And this matrix depends in three angles, three rotation angles, and one complex phase, which is the so-called CP phase. I am going to return to this later. So it's going to be, you're going to learn about that. So here you have some table with the latest measurements. maybe it's an updated, sorry, probably, and I think that is rather well, but maybe some numbers are not updated. So, but in principle, well, you have here the numbers, and we have also part of the picture, the current picture of neutrinos, that we don't know the hierarchy between the mass against state 3 and mass against state 1. So in principle, we don't know if mass against state 3 is bigger than N1 or mass against state 1, or is the opposite. This is the normal and inverted hierarchy. So, well, the future is maybe, is not maybe, the future is the era precision. The future is try to obtain better precision in the measurement of the neutrino parameters, and also to measure very well the CP violation phase. But what is going to be the experimental context of the result that I'm going to show you is some experiment called Dune that is going to be built in South Dakota, in a mine in South Dakota. Is the neutrino being is going to born from in Fermilab, and the neutrino is going to travel 1,300 kilometers. And also in South Dakota, there are going to be there are going to be 4 detectors of liquid argon. We have here some simulation of the liquid argon neutrino interaction at liquid argon, and here some display how works. This is the detector, the main principle of the detectors. And here the neutrino production beam dam arrangement. So remember, only I am going to mention very, very quickly. Remember that I told you that Lederman, Schwarz, and Steinberger was the first to implement this kind of design, a pion, decaying muons, and then neutrinos. So the idea that they proposed, this is still used, obviously with higher intensity in the neutrino fluxes. Well, let's talk about neutrino quantum decoherence. There are very simple examples, or very classic, some classical and one from quantum optics. If we have a mass, oscillating mass in a viscous liquid, he's going to be damped, and this loss of oscillation is a sort of this damping is a sort of decoherence. Also, when we have an atom in a cavity, we are going to have these Rabi oscillations, and this the interaction with the cavity, I mean with the environment, can cause Rabi oscillation. In fact, this is the main problem of the quantum computers, no? That the quantum computers have to deal with. So, which are the standard decoherence phenomena that you are going to find in neutrino oscillation? Well, one is the case when the size of the source of the detection, of the source of the production, the size or the uncertainty of the size is bigger than the oscillation wavelength. So in that case, we raise the oscillation, so we miss the interference, we miss coherence, and this is a way that we can lose coherence. Other way is when, here is when this is again when we do not lost coherence. This is when we are able to see interference. Here we lost the interference. So other possibility is when the mass eigen state, when they travel, the energy of the mass eigen state are much larger. The difference in energy is much larger than the uncertainty in energy. So eventually it will happen if the neutrino travel a very, very long distance. They are going to separate eventually, and they are going to miss interference. Interference is measured as long as they overlap. No, this is the idea of interference. So this is other way to lose coherence in a sort of standard decoherence. Well, what is the case that we are going to discuss, or that I'm going to present? This is the last part of the talk. Is the quantum decoherence in neutrinos, the quantum decoherence. So As I said before, this idea that you have a system, which is with a neutrino system, which is a subsystem within an environment, and this environment is able to interact with this system, and then we are able to lose coherence. So there are some kind of possibilities which this source of the coherence can be originated on virtual black holes in the interaction of neutrino with virtual black hole. Even when they scatter with the black hole, they can be eaten by the black hole, and after they can be re-scattered or re-emitted by the black hole. So there are several options. Well, one is virtual black hole, or other one is fluctuating space-time in the way that we are going to affect the distance between 2 points. No? So the idea of the coherence is going from pure state to mixed state. And this is on an illustration. You have here a pure state, and here you have a mixed state, and we have an harmonic oscillator, an isolated oscillator, and an oscillator with dissipation. No? We have this. No? So here again, we are not going to be we are not going to enter in the detail, but we are going to talk very superficially about the equations. Well, we have a way to deal with this kind of interactions of a system with another subsystem, which is a so-called the open system. Within the open systems, there is an equation called the Lindblad-Maxer equation. When we have here, this part is the regular evolution, the unitary evolution, and this part is a part that corresponds or gives us information about the environment, the interaction between the environment and the system. So the idea is to solve this equation. This is a unitary and non-unitary because it's irreversible. And we can solve these density matrix differential equations, and we can eventually, obviously, calculate it. We are able to calculate the oscillation probabilities. Well, let me give you some what would happen with the coherence. I am going to make a point here, which is very important now. Well, I said that the main mechanism to explain neutrino data is oscillation induced by mass. I said this is the main mechanism. This is the main mechanism. This means that this does not exclude a subdominance mechanism that can be not observed yet because we don't have enough sensitivity in our experiments. This kind of phenomena that I mentioned that was excluded as solution, but not are excluded as a possibility to be a subleading effect not observed yet because our sensitivity is not well enough to see it. So in that sense, I have to make a point that the point of my proposal, of our proposal, is going to introduce this the coherence mechanism not as a solution, but as a perturbation or absolute effect of the mass-induced mechanism of the oscillation. So here is only some history. So as I said at some point, the pure coherence were able to explain Supercambio Cande, also some data from some experiment called LSND were also explained by the coherence, but it was already exclude that kind of solutions, but I am only to give you a context about the coherence. And now, well, our idea is, as I said, is try to test the coherence or the sensitivity to the coherence using Dune, no? Which is not built yet. So the idea is to make projections in Dune if they are able to catch new effects from quantum decoherence affecting the neutrino system. So this is the main idea. And then again, we don't worry about the details. When we discuss in some paper, the probability behavior for some parameters for Dune. In this case, we are using only basically the range, the energy range of Dune. And we found, for instance, that for some parameters of quantum decoherence, when the quantum decoherence is not so strong, the parameter of the intensity of the decoherence is not so strong, we have an energy shift. As long as we increase the decoherence parameter, we are going to get a damping effect, no? as I told you. And here is a formula that we derive to explain this analytical formula. Also, this is a very important point that I'm going to stop a little bit, is something very important when we try to do this kind of searches of beyond standard model physics, is to see how this beyond standard model physics is able to affect our measurements of the standard oscillation, assuming that we are ignoring these beyond standard model effects in the data. So, in other words, we are trying to fit data that include these new effects with theoretical hypotheses based only on standard oscillation. So what we would expect? What we would expect is that we must have a difference between the measurement that we must obtain, because in principle we are ignoring some effect that is going to distort our measurement of the oscillation parameter. And this is something that we are displaying here. Here we are displaying the measurement that you expect without the existence of the coherence. But these parameters are the delta CP and the sine squared theta 1,3. And what we observe is that this is going to displace, as long as we increase gamma, this is going to displace, there is going to suffer a change, the sine squared to theta 1,3. This is the basic message. So you are going to get a distortion on theta 1,3 in your measurement at Dune if the coherence is in the data and you are ignoring the coherence. It could be a hint of something new there if you have this kind of distortion. Well, this is you have the ability of the constrain very well the quantum decoherence, and we have the ability of that depends on, of course, on the model of the coherence that we propose different the coherence matrix shapes of the coherence matrix that explain this. That can produce this kind of limit. Well, which is very interesting is that the coherence implies very rich phenomenology. And one possibility is to observe violation of the CPT. CPT is charge conjugation, parity, and time reversal, which in principle, all the physical laws should be invariant under the combined CPT symmetry at the level of quantum field theory. So, this is not expected, is what I'm trying to say. So, using the coherence, we are going to see that it's possible to have some kind of breaking of CPT violation. And this breaking of CPT violation is measured, is expressed through the probability through this expression, which is the difference between alpha neutrinos, the transition between alpha neutrinos to beta neutrinos. This probability should be different if you have CP violation to antineutrino beta to antineutrino alpha. If this difference of probabilities are 0, so you fulfill the CPT theorem, CPT symmetry. If you have different from 0, you are going to have a violation of the CPT violation, of the CPT symmetry. So if you have survival probability, is going to be neutrinos, the probability to disappear to survival neutrinos, minus the probability to survival antineutrinos. What we observe, where we vary this parameter with energy, motivated by some theories, and then we define a ratio between the difference between the number of neutrinos minus antineutrinos, mu neutrino minus mu antineutrinos. This is the ratio between this difference for oscillation, the standard oscillation plus the coherence, and the standard oscillation. Of course, if the ratio is 1, we don't have any kind of visible violation, no? Visible violation. If this is different from 1, you observe a visible violation. And this is what we observe here. We have here a mountain and a valley, here 1.4 and 0.9 or less than 0.9 here, and delta 0.5 and delta 1.5. So this is so in other words, we have a possibility to observe if some kind of models of the coherence are true and are within the range of Dune, we are going to be able to observe this CPT violation. This is something very similar, but this is only to show you that as long as you increase the coherence parameter, this is the coherence parameter, you are going to get a discrepancy respect the value 1. No, this is only to show you that. I am not going to go more. I don't want to say more about this. This is only that. Well, what is the other point of phenomenology which was very, very interesting in our works that we have found very, very interesting, that also is concerning to CP violation. I am going to explain very briefly. CP violation, you measure CP violation when you make this difference. This is not CPT violation, this is CP violation. If you make this difference between these two probabilities, you are going to find, if it is different from 0, it means that you have CP violation. In fact, if you you use your analytical formula for Bayesian oscillation, you are going to find that this delta P CPV is proportional to sine delta. Remember that I told you about that this delta factor in the PMNS matrix. Well, of course, this appears when you have this. If it is 0, you don't have CP violation. Well, this is a major search, or the most important search in the future for the neutrino experiment, in my opinion, because this can be related with the matter and antimatter symmetry of the universe. So this is very, very important. Now, how is going to be related with quantum decoherence? Wait a few minutes, you are going to learn about that. Well, before, another point that I have, Jorge? I am going to finish. I am going to finish. This is my, I have 2 slides and I'm going to finish. It's fine? Jorge, it's fine?
Fine.
Okay. Okay, only to show you, this is very important. The mass of neutrinos is related, is in principle, you can explain the mass of neutrino with Higgs mechanism, but what is the problem, or what is the something that bothers the physicists is the value that you explain, which is a Yukawa constant. This is the name of the coupling constant of the intensity of the interaction of the massive neutrino with the Higgs. This value is going to be very, very different from the electron coupling constant, Yukawa constant. This is called a natural. Then, for trying to get to formulate a way to formulate a more natural treatment for expressing for generating mass for neutrinos, is you introduce the idea, or Majorana introduced the idea of Majorana neutrino, which is the way that neutrino and antineutrino are the same. So with that, you can explain in a very beautiful way this discrepancy, breaking or erasing this unnatural sync that you have with the Higgs mechanism. Okay, what we have done, what Majorana and CP have to be are related, in which way CP violation of Majorana, how it is related, because in principle, if you have Majorana neutrinos, the PMNs are going to be are going to differ from the Majorana mixing matrix for these phases. If you have a standard oscillation, this is going to be erased. These phases are going to be unobservable. But we have found is that using the coherence, you are going to find terms which are proportional to this phase, Majorana phase. So in principle, what I am saying is that we found that you are sensitive to Majorana phases. You're going to affect the delta P due to the presence of Majorana phases. activated by the coherence. And this is the final slide. So what we have done, we make a projection in two experiments. We compare two experiments. One is Dune, which has a very long distance. Another one is T2 hyper K. In principle, the Majorana phase obtained in T2 hyper K should be not affected by the coherent effect because the distance, because the coherence parameter, here I am quoting, depends on L. I mean, the formulas depends on the multiplication of gamma, the coherence parameter, times L. So if L for the gamma, the limits of the coherence are already excluded the possibility of the coherence in experiment like T2 hyper K because the distance is so short. So in principle, our assumption is that in fact, T2 hyper K have some kind of hint of delta CP. So our hypothesis is that this hint is true, and then we make using that hypothesis true for the delta, we introduce our hypothesis for phi1, and we see that they are going to be, this is a case, this is the cases for gamma 1.5 times to 10 minus 24, and this is gamma for 2.5. And what we are seeing is, as long as we are changing the phase, this is going to be a displace. You are going to find a displace, and this is delta. This is a measurement in theta 1,3 and delta. The basic idea is that you are going to have a displacement in your measurement of delta if phi1, I mean, if Majorana pairs are in nature, and you are ignoring that in your fitting hypothesis. This is the basic idea. And we can see that this discrepancy can be in the order of 3.8 sigma or 5, I can see, 5 a bit more sigma. Okay. The summary is when a signature of presence of new physics is the distortion oscillation parameter. We have seen that in the case of quantum decoherence for sine squared theta 2, 3, and theta. Depending on the model, you expect one or another or both. Constraining the coherence with the Dune is able to constrain the coherence, and also, which is very interesting, is that we can have very interesting phenomenology, very valuable phenomenology that we can learn from quantum decoherence that can give us, for instance, CPT symmetry breaking, or even uncover the neutrino nature. In this case, to discover or uncover the Majorana nature of a neutrino. Well. Muchas gracias. Here is done. Thank you.
Thank you, Alberto, for your presentation. Any question? ¿Algunas preguntas? Pueden hacerlo vía el chat o a través del micrófono.
I have a question. Good afternoon.
Go ahead. Go ahead.
Okay. How can we test supersymmetry at Dune experiment?
Okay. Let me tell you if I got you well. If you can explore supersymmetry at Dune experiment. This is what you said, huh?
Yes, sí, exactly.
Okay. Well, in principle, the natural scenario for looking for supersymmetry are the colliders. But maybe, let me recall, probably indirectly, you can find some dark matter in the beam. You can assume that some kind of dark matter particles that can affect the neutrino beam, and then probably you can relate that with supersymmetry. I'm pretty sure that it's very difficult to have a direct effect in other words, to produce a supersymmetry particle, but in indirect way, probably. Yeah? I am not fully sure about that, but the natural way to look for supersymmetry particles is colliders. LAC, the LAC is the natural scenario, no?
Oh, thanks so much.
There is other question, I guess. Let's see.
Hay
I have a question, sorry.
Victoria.
Good afternoon, Professor.
Good afternoon.
I would like to know if it is possible to consider heavy neutrinos in future.
Okay. Let's, okay, very interesting question. Yes, there is an intense search of heavy neutrinos. The search of heavy neutrinos depends. I mean, of the experiment. In what regard? If you have, for instance, collider, you are going to be able to look for signature of heavy neutrinos of heavy mass. And in the case of a neutrinos experiment, you are going to be limited by for lower mass. But there is intense search for heavy neutrinos. In fact, let me, when I show the seesaw mechanism, I didn't mention any detail, but in fact, the seesaw mention requires a heavy neutrinos, a very heavy neutrinos, in order to explain this very small number that you find for the mass, for the neutrino mass.
So so, thanks, but I have just a silly question, a more silly question. For example, if
there is no silly question.
If we consider, for example, this guy, this heavy guy, you know, and then the matrix of neutrinos is going to increase in order, yeah.
Okay. Yes, but there is the point is that this is a very, very small mixing, no? Okay. Also, this is highly suppressed. This is highly suppressed, the mixing. The mixing of this, you are right. That is very good point. But the point, what I am saying is that the missing matrix elements corresponding to that line, the line that when you include that, are very, very small.
Okay, thanks.
And in fact, this affects the search, because the search, when you try to see the heavy neutrino decay, is suppressed by these mixed elements, no? That I am saying.
I see. Okay. Thanks.
There are more questions, I guess, no? I am seeing Stephen Erazo. Stephen is asking me. He's asking me for the presentation. And Brian is here. Yeah, dependiendo de la naturaleza, I am checking the question in the chat. No, not at all. Okay, Brian, I read your question. Not that it doesn't change. What changed is the phases. What I show that PMNS is going to change. But if we have a standard oscillation alone, I mean, we don't have other way to show up this phase, this is going to be unobservable. These phases are going to be, these are only observable in some process called neutrino less double beta decay that I haven't mentioned. I haven't said anything about that, but this is going to appear that. But no, it's a very good question. No, it's not going to change, because the masses are not going to change. The oscillation wavelength depends on the oscillation wavelength depends on the masses. The masses doesn't depend on the fermionic nature of the neutrinos. It's a very good question. Thank you. And the other question, en el caso de la masa, yeah. Yes, Andres, yes, there are several models. I guess there are several models. The answer is right. You have to check, because there are several options. There are many different versions of the seesaw which generate the same effect, but they're not only including a heavy neutrino. That there are other options to generate the seesaw. But there are also models. I guess that there should be also models with the scalar sector. Yes, of course. Not only that, Jorge, I guess there is no more questions in the chat.
Sí.
Yes, yeah, there is no more question in the chat. You have more questions?
No.
Or it's fine?
Yeah. Okay, entonces, thanks, Alberto, for your presentation. Thank you very much.
No, thank you. No, gracias a ustedes.
Gracias.
I hope that you enjoy the presentation. It was not so bored. No fue muy aburrida. Espero que no haya sido aburrida para ustedes. O sea,
no, claro que no. Claro que no. Gracias, Alberto.
Gracias por la invitación. Muchas gracias por la invitación. Y lamentablemente voy a tener que salir porque estoy así con un montón de compromisos y no he podido asistir va a estar grabado digamos, el meeting. ¿Está grabado? Para ver si lo puedo ver en el futuro.
Yes.
Thank you. It's recorded, so it's recorded. Okay, very good.
Gracias.
My apologies, I have to leave. I have other meetings right now. So, sorry, I'm very sorry. Disculpen, perdónenme, voy a tener que salir. Muchas gracias por la invitación. Thank you very much for the invitation. Bye.
Thank you, Alberto.
Cuídense.